Welcome back to Statistics for Business 1. I'm Shankar, your instructor for the course.
And I'm Liza with 100% probability.
Certainly. In our last segment, we defined what probability meant and answered a few questions that we had drawn up concerning a census dataset that we had downloaded from the UC Irvine Machine Learning Repository.
There are many more questions left.
I agree, it's a long list. As you know, we've laid out the framework of probability using the language of sets.
Sample space, events.
Yes, and once we begin talking about sets, we must think of their unions and their intersections. So in this segment, we consider these against the backdrop of the census dataset. We will describe what joint and marginal probabilities are and of course answer a few more questions on that list. This is quite different from another question we solved in our last segment, which was, what's the probability that a female picked at random from this data set makes over $50K? Dollars, that is.
Really? I'm confused.
True, most of us would be feeling trapped by such language. What we must remember is, a probability is just a fraction.
A numerator over a denominator.
Right. And building it from the statement of the question is what I consider a life skill. It only comes with practice. We must learn to recognize the event and its size goes into the numerator. We must identify the correct sample space whose size goes into the denominator.
It's this simple?
Yes, of course, I'm serious. Examine the first half of our question statement. If we select a row at random from our data set, this means the sample space is all of the data set whose size is, from our pivot table here, 30,160.
Hey, that's our denominator.
Next, the event information is contained within the second half of the problem statement.
Our event is females making over 50,000.
This event, we know from our pivot table, has a size of 1,112.
Hey, wasn't this the same number for the other question?
Yes, let's put everything together and answer our query. If we select a row at random from our data set, the probability that it's a female making over $50K is given by 1112 over 30160, which is equal to 0.037 or 3.7%.
Males have it way better.
You might be thinking it's so unfair, but there's one fact we must observe. The ratio of females to males in this data set is 9,781 to 20,379, which is nothing but what's in this last column over here, or approximately 1:2.
Even if I were to double things, it would be 7 versus 21.
Now you're thinking like a quant. There may be many more factors at play like education level and so on. So advanced techniques like regression help us control for these factors and suggest what to expect. Then we would be stating the probability of randomly selecting a female making over 50K from this data set as 1112 over 9781 instead of 1112 over 30160, which is the right answer.
That's a colossal mistake.
I'm afraid so. I've drawn a Venn diagram to illustrate our situation here. Because males and females are disjoint, we have chosen to use rectangles to denote the sets. The diagram is approximately drawn to scale. The overlap regions are what we must focus on. Using our set notation, the event E is nothing but F intersection O. This is the olive portion of our diagram with a size of 1,112. The joint probability of two events A and B is the probability that the event A and the event B occur simultaneously.
That's an intersection.
Right. And the likelihood that a randomly chosen person from this data set is a female making over 50K is given by, you guessed it, PF intersection O, which is nothing but a joint probability. Now, why don't you get some practice with this? Compute the joint probability PM intersection O. Can you? An intersection of events may well be empty. Look at our data set where males and females occupy separate rows. Such events are called mutually exclusive events. Lisa, give me another example.
How about those who make over $50,000 and those who don't?
Yes, you got it. Our pivot table is an example of a contingency table which lists out different values of two variables and provides the corresponding counts. Now these counts are large numbers, so for us to get a better hang of them, we convert them into proportions just by dividing every entry with the size of the sample space. The highlighted cells are all joint probabilities and they all add up to 1 as we would expect. We'll go over this in much more detail when we discuss random variables. So Lisa, what's with the 0.46 entry in the table?
It is the joint probability of a randomly chosen row from our data set representing a male as well as someone who makes less than $50,000.
This is nothing but the intersection of F complement with O complement.
Males complement females.
Why not? You might have derived a result in your school days that F union O complement can be expressed as F complement intersection O complement. Now we can visually verify that the complement of F union O consists of males making less than 50K,
whose probability is 0.46 as we just saw.